Hello everyone, thank you for attending this talk. I am Patricio Moreno from the Laboratorio de Automática y Robótica at the Universidad de Buenos Aires and CONICET. In this work, we present a formulation based on a team of unmanned aerial vehicles for the application of aerial cinematography. The team is envisioned as a fully articulated multi-camera ship crane, which is described using the cluster space control formalism. An optimization-based controller computes the control inputs and commands the formation to take the desired shots while actively avoiding collisions and camera's mutual visibility. I'm going to show two different cluster state representations to illustrate this approach, and finally, to validate our scheme, I show three different simulations using these representations. Recently, unmanned aerial vehicles have been used for filming in many scenarios, and the applications continue to grow. There is a genuine interest both in the academia and industry, and a lot of effort is being put into autonomous cinematography. UAVs not only can be used to generate the same type of shots that are available with traditional equipment, but they also enable new ones while speeding up filming times and potentially reducing cost compared with helicams and spidercams. It is of special interest to consider applications where not one but a team of UAVs is given such a task. For this, we think of multiple UAVs as the unarticulated multi-camera ship crane, which can be remotely controlled by one or more operators. In our setup, the ship crane can follow predefined trajectories given by artistic guidelines, but it can also be commanded to fine-tune what the cinematographer wants to show. While doing so, it should also be able to avoid collisions and mutual visibility of the other cameras. The cluster space formulation is a technique that allows simple specification of the motion of a group of robots, and it is versatile in the sense that the state's definitions can be changed depending, for example, on the desired type of shot. This formulation allows to work with application-oriented parameters for both specification and control. To get an insight on how the cluster space formulation operates, we can think of a simple scenario where a group of free ground vehicles should maintain a triangle formation. This group forms a cluster of robots for which new states are defined. For example, we can use the triangle size orientation. The original states of each robot, which are defined in the robot space, relate to the states in the cluster space through the forward and inverse kinematic functions. These functions define the mappings between both configuration spaces. The tangent spaces of these manifolds can be related using the Jacobian matrices of each function. So it is easy to translate velocities in the cluster space to velocities in the robot space and vice versa. This notion is key to build a cluster space kinematic controller. To control such a formation, we proposed a closed-loop control strategy using cluster states defined for the application and the desired type of shot. The controller is based on an optimization problem which is solved simultaneously for all the agents in the formation for a finite time horizon with fixed time steps. Assuming stabilized UAVs, vehicles with 4 degrees of freedom, X, Y, and Z axis, and the yaw angle, each with a pan tilt camera, this type of controller is suitable. To do so, we define 3 different cost functions that account for different aspects of the problem, namely an artistic cost function, an aiming cost function, and a smoothness cost function. Using this, we solve a minimization problem for the weighted sum of each of these functions, subject to constraints defined by the vehicle dynamics, mutual visibility avoidance, collision avoidance, and bounded control inputs. The artistic cost function penalizes deviation from the intention of the director of photography. These artistic guidelines include predefined trajectories and viewpoints, and velocity commands that are used for online fine-tuning of these trajectories. The aiming cost function weights the error of each agent in aiming at the point of interest. And finally, the smoothness cost function is used to penalize large magnitude control signals and, using a discrete difference operator, penalizes jerky movements. Because the minimizing solution lies in the cluster space, it has to be transformed into commands for each UAV and the gimbals through the aforementioned formalism. To ensure that the mutual visibility is avoided, the framed inequality must hold, where gamma is the field of view, n is a unit vector normal to the image plane of the camera, and p is a unit vector that points from one vehicle to another. The collision avoidance constraint is straightforward. The distance between vehicles must be greater than a safety radius, and it also considers the distance from each vehicle to the point of interest. For the mutual visibility avoidance constraint, we define a right cone with its apex at the camera, its axis aligned with the image plane normal, and its angle equal to the field of view of the camera. Typically, image sensors are rectangular, so the approximation using a cone won't handle correctly objects that may project to the sensor but are considered outside the cone. If this is in fact an issue, a simple solution is to enlarge the field of view to consider the length from the image center to one corner, although this approach would force the exclusion of objects in areas that do not project to the image sensor. We first present a formation for n UAVs in a cluster state definition that mimics a leader-follower configuration. This strategy can be seen as a particular case of the cluster space formalism. The state definition includes the spherical coordinates of each UAV with respect to a virtual leader and the normal of each camera's image plane. Nonetheless, our approach is oriented to applications in which the number of UAVs is fixed, known, and relatively small. In this case, we consider a cluster state representation with two UAVs, which can be used to define a segment with each UAV at the ends. Filming scenarios where 2 or 3 cameras are used is common, and many applications can benefit using this definition. It should also be noticed that the problem constraint can be easily expressed in terms of the cluster state. The simulation testbed consists of a small quadrotor that acts as a point of interest and a cluster of hexacopters with pan-tilt cameras with a configured field of view of 60 degrees, although it's in reality of 120 degrees. The reduced field of view allows us to see on video the behavior of the UAVs as they approach Adler's field of view. For all these vehicles, the stabilizing controller is DPX4 autopilot, which runs within a ROS kinetic environment and is simulated using Gazebo 7. The proposed controller was implemented in Python using SciPy sequential least squares programming method and runs on a ground station computer which communicates with the vehicles using a Mablink interface provided by the Mavros package. The system runs inside a container within the OpenUAV simulation testbed of the Arizona State University in the United States. The first video shows a cluster of 2 UAVs doing an orbital motion at a fixed altitude aiming at an ascending UAV, which is our point of interest, and their respective first-person view shots. This scenario stresses the system as the point of interest reaches the same altitude as the cluster because the aiming function will try to center the point of interest in the image, a situation that would violate the MBA constraint, so the controller must perform a great deviation from the artistic trajectory. The inset on the upper right corner shows the angle of interest between the aiming vectors and the UAVs, and the aiming vectors and the point of interest. The blue line must not cross down the dashed field of view line, as it means that the MBA constraint would fail, and the orange line crosses the field of view line if the point of interest gets out of the field of view. This may happen as we consider the aiming a cost and not a constraint. The second and third tests are similar between them. Both videos present the results in a similar fashion as the first video, considering now a formation of 4 UAVs and a static point. The formation has to do another orbit in motion, but in this case, the point of interest is further away and not at the center of the formation. It can be seen that the controller moved the UAV-4 out of its predefined trajectory. The FPV shots show how the UAVs maneuver to evade the field of view of the other cameras, even at high speed. However, it must be pointed out that for the higher speed, there are intervals where the MBA constraint does not hold, and this is due to the lack of a safety radius to contemplate position uncertainties and because of the fixed time steps used in the optimization horizon. For these time steps, the constraint holds, but does not hold between these time steps. Thank you for your attention. I'm open to questions and feel free to contact me at the provided email.